Let's talk about writing two-dimensional vectors in Cartesian or rectangular components. Recall the formulas for sine, cosine, and tangent for a right triangle, sometimes remembered by their acronyms. A vector f has both magnitude and direction. For the Cartesian, orthogonal xyz coordinates form of the vector f, write as addition of two vectors pointing in x and y directions. We write this as the sum of two components in the x and y directions, a magnitude f of x in the x direction defined by the unit vector I hat, and a magnitude fy in the y direction multiplied by the unit vector j hat. For vectors in the 2D plane, there is no vector in the z direction out of the 2D plane. We recall that unit vectors I hat and j hat point in the x direction and y direction. The unit vector out of the page in the z direction is called k hat. Magnitude of the unit vectors are equal to 1. By multiplying by a unit vector, we give the magnitude a direction. F of x times I hat assigns the x direction to fx. F of y times j hat assigns the y direction to fy. In this figure, we write the fx and fy components as the adjacent and opposite sides of a right triangle with angle theta and a hypotenuse given by the magnitude, the length of vector f. From the definition of cosine as adjacent over hypotenuse and sine as opposite length over the hypotenuse, we can express the adjacent side f of x and the opposite side f of y in terms of the magnitude f and cosine and sine of the angle theta. Substituting these trig expressions into the Cartesian form of the vector f, we can write the vector components f of x equal to the vector magnitude f times cosine of angle theta and fy equal to the f magnitude times sine of theta. Now let's do a quick example. Let's take the magnitude of the vector to be 25 pounds and the orientation angle theta with respect to the x-axis by 40 degrees. Evaluating the numerical values, we find f of x equals 19.15 pounds and f of y equals 16.07 pounds. Looking at the significant digits, we could safely save the final answer as approximately 19.2 pounds and fy equal to 16.1 pounds. We can sketch this result to see if our answers are making sense. Since the 40-degree angle is less than the half angle of 90 degrees for the right triangle, that is less than 45 degrees from the x-axis, we expect the f of x component to be greater than the f of y component. So our answers do make sense. We can further check this by using Pythagoras' theorem to compute the length of the hypotenuse from its adjacent and opposite components. The components f of x and f of y can also be used to compute the angle using either arctangent or arccosine to confirm that theta is indeed 40 degrees as we initially specified. In the two dimensions, the vector can be represented by a magnitude and a single angle defining orientation. Here we've written the arrow over the notation f to denote the vector with both a magnitude and a direction. In 3D, we will need at least two angles to find orientation. Here we show that given the magnitude f and orientation angle theta of the 2D vector, the Cartesian components can be computed using MATLAB using a single line of code. The variable f vector is assigned the value of the row vector array, computing the multiplication of magnitude f times the vector array, defining the 2D unit vector with components cosine theta and sine theta. In MATLAB, vectors are represented by an array indicated by the brackets, with commas separating the two components. The notation cosine d and sine d is used to tell MATLAB to compute the cosine and sine functions in degrees instead of radians. Thanks for watching, and good luck in the rest of your studies.